Hi, hello everyone. We were discussing about magnetic effect of current and in that Biot-Savart's law and its applications. Already we discussed magnetic field due to a long straight current carrying conductor. So today's sessions we are going to discuss magnetic field on the axis of a circular current loop. So how the magnetic field will calculate in a circular current loop, that we are going to discuss. This is the schematic diagram for finding the magnetic field of a current carrying circular loop. See, here we are considering a circular loop. Okay, I current is passing through this. It is the current is passing inward. Okay, sorry, outward. Current is passing in this direction. See, here center O, from center O to this axial line, we are considering a point P. And let the plane of the loop be perpendicular to the plane of the paper. The plane of this loop is perpendicular to the plane of the paper. So to find the magnetic field at an axial point P, this is the axial point P. Here we are considering the point P at a distance x from the center O. Here, in order to find the field here, we are considering a small elemental section here. XY is the elemental section here. So we are considering this elemental section dl, having magnitude dl. Okay, here see, r is the position vector of the points C and P. So here r is the position vector of the point P relative to the element dl. Okay, so then according to Biot-Savart's law, magnetic field at P due to this dl, how we can write that? dB equal to mu 0 by 4 pi I dl sine theta divided by the position vector is r, small r square. Okay, see here dl and this r vector is perpendicular. dl perpendicular to r. So here theta will be 90 degree. Okay, see, consider this as a circular loop and this dl vector is in this direction. Okay, dl vector is in this direction and this r vector is in this direction. So this will come like this. See, if I am holding like this, this will come like this. Okay, so this angle here, we will get one angle. Okay, this angle will be 90 degree. So that's why it is 90 here. If you are considering this triangle, this won't be 90. Okay, so here we are considering only these two. First is, one is, this is our dl vector and this is r vector. So that is in a slanting way. It will be like this only. Like this, it will be slanting. Okay, so here we are considering this as 90 degree. So this equation will become dB equal to mu 0 by 4 pi I dl divided by r square. So here this dB lies in the plane of the paper and is perpendicular to r. Okay, and dB is also perpendicular to r. So here we are taking the component of dB. So here in this axis, along the axis we will get dB sin theta and perpendicular dB cos theta. So now we can write this as dB along the axis, along x axis I am taking dB sin phi and dB perpendicular is dB cos phi. These are the two components we are getting. Okay, if we consider an elemental dl here also, if I am taking dl dash, okay, in the bottom of the loop I am considering another elemental area dl dash. Then the perpendicular components, these two perpendicular components will get cancel each other and the axial components gets add up. So here the axial component is dB sine phi. So it will get add up. So we can write the total magnetic field at the point P in the direction of this CP. In the direction of this CP, this direction. How we can write this? Total magnetic field B will be equal to integral dB sine phi, right? So from this we need to find sine phi. So if this is phi means, how we can find sine phi? Sine phi equal to this divided by this. Okay, so r divided by small r. Okay, so we can write this as B is equal to integral mu 0 by 4 pi I dl by r square into capital R by r. So this will be mu 0 I r by r square into r cube. So 4 pi r cube integral dl will come. So what is integral dl here? Integral dl, which is the circumference. So here circumference is 2 pi capital R. So here we can substitute capital R. So we will get mu 0 I by 4 pi R square divided by R cube. After substituting integral dl is equal to 2 pi capital R. Then B will become mu 0 I R divided by 4 pi small r cube into integral dl is 2 pi capital R. Here we will get B is equal to mu 0 I r square divided by 2 into, what is r here? Small r, root of r square plus x square. So we will get r square plus x square the whole raised to 3 by 2. So this is the equation for magnetic field here. Okay, so here the direction is along the positive x direction. So we can write this as B is equal to mu 0 I r square the whole divided by 2 into r square plus x square the whole raised to 3 by 2 into I cap. Like this also we can write. Again, if the coil is having n turns, then this equation will become B is equal to mu 0 n I r square divided by 2 into r square plus x square the whole raised to 3 by 2. Just we add one n in this. Okay, so this is the final equation for magnetic field on the axial line of a circular current carrying loop if the loop is having n number of turns. Okay, so here we have some special cases. First case is at the center of the current loop, that is the distance x is equal to 0 at the center of the current loop. So x is equal to 0 means our equation will become B is equal to mu 0 n I r square divided by 2 into r cube, r square plus x square the whole raised to 3 by 2. So in that x is equal to 0. So it will become r cube. So the equation is mu 0 ni divided by 2r. Again we can write this. If area is pi r square, area of the loop is pi r square, then we can write this as mu 0 n I a divided by 2 pi r cube. This also we can write. So the field is directed perpendicular to the plane of the current loop. Okay, this field is directed perpendicular to the plane of the current loop. So next is at the axial point lying far away from the coil, that is x is greater than r. That is the distance between axial point and the center is greater than the radius of the loop. Then how we can write this? B will be equal to mu 0 ni capital R square divided by 2 into R square plus x square. So x is greater. So this will become 2 x cube, or which can be written as mu 0 ni a divided by 2 pi x cube. Okay. So here, what is the field here? The field is directed along the axis of the loop. That is, we can write this as here B is proportional to 1 by x cube. B is proportional to 1 by x cube. So if x is, the distance is more, increases means, then B will reduce. Next is case 3. At an axial point at the distance equal to the radius of the coil and x is equal to r. So what will happen there? R square plus, instead of x we can substitute r square. So it will be mu 0 ni r square divided by 2 into r square plus r square the whole raised to 3 by 2. So this will become mu 0 n I r square divided by, here it will be 2 into, we will get, here it is 2 r square. So 2 raised to 3 by 2 into r cube will come. So finally this will be B is equal to mu 0 ni divided by r square r cube get cancelled. We will get 2 raised to 5 by 2 r. So at an axial point at the distance equal to the radius of the coil means magnetic field will be mu 0 ni by 2 raised to 5 by 2 r. So these are the 3 special cases in this session. So next is the variation of magnetic field along the axis of a circular current loop with distance from the center. Okay, this is our center O. So this is the radius we are taking. So the graph will go like this. So the maximum field will be at the center of the coil. Maximum will be at the center of the coil, and it is decreases when as we go away from the center on either side of the loop. Okay, this is the variation of magnetic field. Next also we are taking some cases, magnetic field due to a circular arc. See, here we are considering a circular arc having angle theta. This angle is theta. I am taking a current element here dl. So I current is passing through this. So magnetic field at the point O. At this point I need to find magnetic field. This is point O. Okay, so for that we can write this as dB is equal to mu 0 by 4 pi I dl sine, this will be 90 degree. With this will be 90 degree. So sine 90 divided by r square will come. So mu 0 by 4 pi I dl divided by r square. So the total field will be integral dB, right? So this will be mu 0 by 4 pi I by r square integral dl. Okay, so this will be mu 0 by 4 pi. What is integral dl? That is L only. I by r square into L will come. See, from this figure, what is the angle theta? Theta is equal to arc by radius. Arc is the total length, that is L, divided by radius r. If it is having radius r, okay, total length is L. So theta is equal to L by r, or L is equal to theta into r. We can substitute here, right? So mu 0 by 4 pi I by r square into theta r will come. So the final equation will become B is equal to mu 0 by 4 pi I theta divided by r. So this is our final equation for a circular arc. Okay. So next case we are taking is a semicircular loop. Here also we need to find the magnetic field. Okay. So here we are taking this as radius r. Okay. I current is passing through this. So if I am taking an elemental area here having magnitude dl, I current is passing through this. So magnetic field at the point O, we need to find the magnetic field here. Okay, so magnetic field at the point O, dB equal to mu 0 by 4 pi I dl sine, here also theta is 90 degree, sine 90 divided by capital R square, that is the distance. So this will become mu 0 by 4 pi I dl divided by r square. What is B here? Total magnetic field there, mu 0 I by 4 pi r square integral dl. Here what is integral dl? Here it will be L is equal to pi r. So here B will be equal to mu 0 I divided by 4 pi r square into pi r. B will be equal to mu 0 I divided by 4 r. So this is the magnetic field of a semicircular loop. Okay. Next, if we are considering a quarter arc, here this is the radius, I current is passing through this. So I am taking an elemental length dl here. So here also dB we can write this as dB is equal to mu 0 by 4 pi I dl divided by r square. Magnetic field will be inward here. Okay, so B is equal to integral dB will be mu 0 I divided by 4 pi r square integral dl will come. The same method we are using here. But here what is L? L is equal to pi r divided by 2. L is pi r divided by 2. So B will become mu 0 I by 4 pi r square into pi r divided by 2. So the final equation will become mu 0 I divided by 8 r. Okay, this is the magnetic field due to a quarter arc. Again, we are taking 3/4 semicircular arc. Okay, so here, what is this angle? This angle will be 2 pi, right? Then here we can take dB is equal to mu 0 by 4 pi IDL by capital R square, or B will be equal to mu 0 by 4 pi R square integral dl, that is L. But here we need to find L. L is equal to here 2 pi minus pi by 2. 2 pi minus pi by 2 into R will come. Or we can write 3 pi by 2 R. Here I am substituting 2 pi minus pi by 2 R. What we will get? 3 mu 0 I divided by 8R. So this is the equation for 3/4 semicircular arc. Okay. We can do some numericals here. See, the first problem. The plane of a circular coil is horizontal. It has now 10 number of turns. So n is 10. Each of radius 8 centimeter. So capital R is 8 centimeter. A current of 2 ampere. So I is 2 ampere flows through it. The current appears to flow clockwise from a point above the coil. Okay, it is moving in clockwise direction. Find the magnitude and direction of the magnetic field at the center of the coil due to the current. What is the magnetic field at the center of the circular coil? We have B is equal to mu 0 Ni divided by 2R. This is the magnetic field at the center of the circular coil. So it is given N is equal to 10, R is equal to 8 centimeter. So it will be 0.8 meter, and I is given as 2 ampere. Right? So we can substitute directly. 4 pi into 10 raised to minus 7 into N is 10 into I is 2 ampere divided by 2 into 0.08. So the final answer will be 1.57 into 10 raised to minus 4 Tesla. This is the magnitude. So the direction of magnetic field at the center of the coil due to the current. What is the direction? Current is moving. Here it is given the current appears to flow clockwise from the point. So the current is, if the current is in clockwise direction, the magnetic field at the center points vertically downwards. It will be vertically downwards. The magnetic field will be vertically downwards. Okay. Magnetic field will be vertically downwards. Okay. See, next problem, second problem. In the Bohr model of hydrogen atom, the electron circulates around the nucleus in a path of radius 5.1 into 10 raised to minus 11 meter. So the radius is given, r is equal to 5.1 into 10 raised to minus 11 meter. Okay, then at a frequency 6.8 into 10 raised to 15 second, frequency nu is given as 6.8 into 10 raised to 15 second inverse. Find the magnetic field. We need to find B set up at the center of the orbit. At the center of the orbit, we need to find the magnetic field. So here we don't have that I. Current is not given. So we need to find current. So how we can find current? Is there any relation between current and frequency? Yes. I is equal to nu E. I is equal to nu E. How it is coming? This will come like this. Current is equal to charge by time. Here we are taking the charge as electron charge and time is taking as time period. So E into what is 1 by time period? Frequency. So E nu. Okay. So when we are substituting in this equation, what is nu here? 6.8 into 10 raised to 15 into charge of electron 1.6 into 10 raised to minus 19. So here we will get 6.8 into 1.6 into 10 raised to minus 4 ampere will come. Okay, so we can put like this. And what is B here? We got I. So we can write the equation for magnetic field as mu 0 I by 2 R, right? So 4 pi into 10 raised to minus 7 into 6.8 into 1.6 into 10 raised to minus 4 whole divided by 2 into 5.1 into 10 raised to minus 11. So after calculating this, we will get 13.4 Tesla. This is the magnetic field at the center of the orbit. Our third problem, a circular coil having 100 turns. So N is given as 100 turns of radius nearly 20 centimeter each. Here capital R is 20 centimeter, or we can write this as 0.2 meter, right? Then magnetic field at the point, coordinate is given, XYZ coordinate is given as 0, 0, 20, root 3. Okay. So we need to find here magnetic field at the point this, that is it is in Z direction. When this coil carries a current of 2 by pi. So I is given 2 by pi ampere. Okay, so what is the magnetic field at the axial field point? Already we derived, right? B is equal to mu 0 n I r square divided by 2 into r square plus x square the whole raised to 3 by 2. So we can substitute in this. We will get B is equal to 4 pi into 10 raised to minus 7 into n is 100 turns into I is 2 by pi into r is 0.2 the whole square, the whole divided by 2 into 0.2 the whole square plus point, here we are taking this instead of x we are taking z, so 0.2 root 3 the whole square, the whole raised to 3 by 2. So this will become 4 into 10 raised to minus 5 into 0.044 divided by 2 into zero point 0.2 cube into 1 plus 3 the whole raised to 3 by 2 will come, which is equal to 0.16 into 10 raised to minus 5 divided by 2 into 0.008 into 8. So this will be 25 into 10 raised to minus 6 Tesla, or we can write 25 micro Tesla. This is the answer for this problem. Fourth problem. Two coaxial circular loop L1 and L2 of radii 3 centimeter and 4 centimeter. For this 3 centimeter and this is 4 centimeter radii placed as shown in the figure. What should be the magnitude and direction? We need to find the magnitude and also direction of the current in the loop L2 so that the net magnetic field at the point O be 0. Net magnetic field we need to find. It, uh, it, it will be 0. Okay, so when the magnetic field will be 0, D at O is 0 when the current in L2, if this current is in this direction, then this current should be in this direction. It should be opposite to that of L1. Then magnetic field will be 0. So we can write this as B magnetic field due to current I1 is here and current I2 is here. B due to I1 in L1, which is equal to magnetic field due to I2 in L2. So here we will get mu 0 I1 R square divided by 2 into R1 square plus X1 square the whole raised to 3 by 2. This will be equal to what? Mu 0 I1 I2 R2 square divided by 2 into R2 square plus X square the whole raised to 3 by 2. Okay, so this will be mu 0 I1 into 0.03 centimeters, so 0.03 square divided by 2 into 0.03 the whole square plus 0.04 the whole square the whole raised to 3 by 2. This will be equal to mu 0 I2 into 0.04 the whole square divided by 2 into 0.04 the whole square plus 0.03 the whole square the whole raised to 3 by 2. From this we can find I2 as 0.03 the whole square divided by 0.04 the whole square into I1. Already they give I1. What is I1? 1 ampere. So we will get I2 equal to 9 by 16 into 1 ampere will come. So this will be 0.5, 0.56, 0.56 ampere. Hope you understood the sessions very well and able to do the numericals also. We will discuss the rest topic in the coming sessions. Thank you.